Hello and welcome back. This will be the third and final video on section 2.4, and in this video we'll talk a little bit about p-values, which will show up later in the class, and I'll also mention regression, which will also show up later in the class, in fact in chapter 10, in the last chapter. So p-values are often going to be used instead of the value r, which was the linear correlation coefficient. So R is what sort of explicitly tells us whether or not the data is going to be linearly correlated or not. P is going to be deduced from R. You'll be able to calculate P using R, but we're not going to talk about how to calculate P right now, just how to interpret a value if you were given one. And essentially P gives the same information as R. You use R to calculate P in this instance. And P, in this terminology, we can kind of think of P as standing for percent, and it tells you how likely, P should stand for probability. It tells you how likely the data could have occurred in sort of a random situation. So when you're given two scatter plots and you look at them in this first scatter plot, you can see that the data looks like it's sort of arranged somewhat randomly, and it seems fairly likely that if you just picked some numbers at random, that this could have happened. So here, the p-value is high, because the probability that this could have happened is pretty high. Whereas over here, this looks pretty linear, and if you're just choosing numbers at random, it seems somewhat unlikely that you would get this linearly correlated data. So here, the p-value is low, as in there was a low chance, there's a low probability that this could happen. So because it did, that means something special happened. Probably the variables are correlated. Whereas over here, this could have happened randomly, so it doesn't seem very likely that anything special happened, and it doesn't seem likely that the values are correlated. So again, P is going to range from 0 to 1, and essentially we can interpret it as a percent or a probability. So for example, if we were looking at some correlation and we calculated P to be 0.65, this means that our linear correlation coefficient, so R, for that data, had a 56% chance of occurring, that's not how you spell occurring, and that seems pretty high. That could have happened randomly. The correlation coefficient that we calculate, the R value, had about a 50-50 percent chance of actually occurring. So because this is high, we can't say that the data is going to be linearly correlated. It seems pretty likely that it might not have been. So in general, we would need a p-value of less than 0.05, meaning less than a 5% chance. And once we're this low, we can say that's so unlikely from happening. We can say that the data is probably linearly correlated. So if P is bigger than 0.05, you can say, well, it could have happened. It could have just randomly happened that we got the data that we did. So we need a p-value of less than 0.05 to be able to say the data is linearly correlated. Any bigger, we can't say that. So once we go through all the steps to determine whether or not data will be linearly correlated, if we find that the data is linearly correlated, there will be a line that we can draw through the data. So for example, over here on the left, we have some data. It looks roughly linear, so I should be able to draw a line that approximates where the data is. It's not perfect. We have data points that occur off of the line, but everything seems pretty close. In data that's not correlated, it's hard to draw a line. Is the line that goes through this something like that? Well, maybe, but it might also be something like this, or even steeper. And choosing a line doesn't really work. So ultimately, when we have linearly correlated data, we can draw a line through it, and we can use that line to try to describe the data. So the equation that we use will be this one, and we will see this in chapter 10. So for the moment, we're not going to do much with regression. I just want to show you it now. And this equation should look a lot like y is equal to mx plus b, which you'll probably have seen before when describing a line. M is the slope, and b will be the y-intercept. And all we've done is we've rearranged it. So we put the term with an x last, the constant term first, and we've renamed some things. So we have b0 and b1. There are reasons for this, just to make things a little bit consistent, but they are the same equation, just rearranged. So for instance, in this line, where the line meets the y-axis, this will be b0, and the slope of this line, how steep it is going to be b1. So b1 is going to be how steep that line is. So all we have to do is figure out where does the line hit this axis, and how steep is it, and that will give us the formula for the line. But we'll see this in chapter 10, and we'll see p-values throughout the book, in particular once we get to hypothesis testing.